Hi guys, welcome to my channel, and today I am going to talk about free vibration with Coulomb damping. So today I'll be talking about what is a friction force, how does it affect our system of vibration, and I will also implement the governing equation both in a MATLAB M file as a code, and also I will simulate the system in Simscape. So stay with me. If you have seen my previous tutorial there, I talked about free vibration with viscous damping. But in that tutorial, when the mass was sliding over a surface, this surface was assumed ideally frictionless, which is a good assumption in some of the cases. But, in real life, there always exists some friction. So today I'm going to talk about how to add the effect of dry friction to your vibrating system. So the dry friction or Coulomb friction force is equal to mu times n. And mu is the coefficient of kinetic friction, which is a constant value, and it depends on the quality of the surface or the surface finish or the materials. For example, if it is a metal over metal, you expect the mu to be equal to something between 0.1 up until 0.3, depending on whether it is lubricated or not. But n is the normal force. And if you look at this free body diagram, you can see that when you have a mass equal to m, there is a weight force downward, and it is cancelled by a normal force upward. So n is equal to w in this system. So the normal force is equal to the weight, which is equal to mg. And the friction force is equal to mu times n. So n is equal to mg, and friction force is mg times the coefficient of kinetic friction. But how about the direction of this friction force? The direction of this mass can be displayed by its velocity. So x dot here means velocity. And when the velocity is in the right direction, it means this mass is moving in this direction. And the friction is always a resistive force, so it is in the opposite side. So mu n here is in the negative direction. But if the mass is moving in the left direction, then the friction force is going to be in the right direction. So it is always resisting the direction of movement. Now we're going to move forward and write the equation of motion. You can see there are two cases. You can suppose that the spring force can be in the same direction as the friction force. But there is another case. The spring force is in the opposite side to the friction force. For example, suppose this is the equilibrium situation of a mass and it is moved to the right side in this direction. So when it is moving to the right, the friction force is to the left. It is resisting the right side movement. And also, the spring is trying to move the mass back to its equilibrium position. So both of the friction and the spring force are in the left side. So they are adding to each other. It is going to be case 1. But when this mass is at this position and it is moving to the left side, then the friction force is going to be to the right, and it is going to be in the opposite side than the spring force. So that is when you have case 2. And as you can see, for each half cycle, we have to write a different equation of motion, since the direction of friction force changes after each half cycle. But using the sine function, we can come over this problem. Both of the cases can be put together in a single equation of motion using the sine function. And as in the previous tutorials, we have ma for the inertial force, and kx is the spring force, and mu n is the force of friction, which is multiplied by the sine function. And when I'm going to start coding, I will show you what this function does. And I also have to explain the state space form of the equation of motion, because we are going to need this form of equation to implement it in MATLAB. So x double dot is equal to this. So what I did is basically I moved these two terms to the other side of the equation and I divided the whole equation by m. So I came up with this equation. I take my state variables to be x and x dot, and so y dot is going to be equal to this form. So x dot is already one of my state variables, so I don't need to change it. But x double dot has to be written in the form of these two state variables. And this is going to be the formula. So now I am going to move to MATLAB and start coding Coulomb vibration. Okay, so suppose you have this problem. You have a mass equal to 2 kilograms. And you have a spring with a spring coefficient equal to 200 newtons per meter. And the gravitational force is equal to 9.81. And the friction coefficient is equal to 0.1. And the initial displacement is equal to 10 centimeters. So I write it as 0.1 meters. I want to solve this system under free vibration with Coulomb damping. And I'm going to use ODE 45 function for that matter. So as always, I start with closal clear CLC. You know, in the previous tutorials, I used the solve command to solve the equations analytically, but this equation that we are going to solve here, it has a sine function, and this sine function adds a discontinuity to your equation. So you cannot expect to find an analytical solution for this equation. But we can solve this equation numerically, and that's what I'm going to do using ODE 45 function. And if you are not familiar with ODE 45, please check my other tutorial regarding that. So time and the state variables are going to be equal to ODE 45 of at sign f, and f is going to be a function containing the equations. And I want to solve this equation from 0 to 10 seconds. And the initial conditions was, as I said here, the initial displacement is 0.1 and the initial velocity is equal to 0. So I have to define function f, which is the function of t and y. And I name the output dy dt. So I need to define all of these constants in my function. And I define n, and I set it to be equal to m times g. So what is my equation? This is the equation I want to implement, and it says dy dt, or y dot, dy dt is equal to x dot and this term. So y is consisted of these two terms, x and x dot. So since MATLAB is not aware of x and x dot, this value is called y1 and this value is called y2. So these are the first and second arrays of y. So dy dt is going to be equal to y2 and negative k times x over m. Again, instead of x, I have to write y1 over m minus mu. So instead of mu, I have to write mu. Mu times n over m sine of y2. And before I continue, I want to tell you what is the sine function, which in MATLAB it is displayed as sine. So I type help sine, and here is the definition of this function. For example, sine of 10 is 1, sine of 12 is 1. Any positive number, for any positive number, this function gives 1. And for any negative number, sine -5, it gives -1. So you can also plot, I say f plot at sine from, not from, okay. I plotted here. And here's the function. I set the axis equal to -10 to 10 and -2 to 2. You can see this is the sine function, and there is a discontinuity at 0 point. As I said, this is why we cannot solve that system of equation in dsolve command analytically. Let me run this code to see if I face any errors. Okay, I forgot to terminate this statement, so I put a semicolon at the end of it and ran it again. Okay, run with no errors. So I plot t comma y of the first column. So this is time and this is the position. If instead of 1 I write 2, it is going to be the velocities, but I want the positions. Now we run it, and here is the position of the vibrating mass with respect to time. And I want to add a few comments on that. So if I connect the peaks of this figure, I can see that the amplitudes are decreasing linearly. As you probably remember, in the previous example, in the viscous damping example, the amplitudes were decreasing exponentially, but in the Coulomb damping, they are decreasing linearly, and that is one difference. Also, you can see the mass is going to stop oscillating at some point. So when it reaches this value, -2 times 10 to the power of -3, it is going to stop moving. And this is opposed to the viscous damping example, when the oscillations were going, theoretically, they were going on forever and forever. But in Coulomb damping, at some point, the mass is going to stop vibrating. So I open Simulink and create a blank model. Then I will look for Simscape under library browser. Under foundation library, I find mechanical, and I'm going to have a translational system. So I add a mass, a translational reference, a translational spring, and a translational friction. I press Ctrl I, and as always, I connect the C ports to the reference. Again, Ctrl I, and this goes here. Then Ctrl Shift R, and the mass is connected to these two ports. Also, I need a solver configuration block in any Simscape system, and I also want a mechanical sensor. So I add an ideal translational sensor. I double click on it and set it as an absolute sensor. I do not want velocity, only position is fine. And as I said, the initial position is 10 centimeters, so 0.1 meters. I set it both for my sensor and for my spring, 0.1. The spring constant was 200 newtons per meters, and the mass was 2 kilograms. So I connect, I add a PS Simulink converter, and I add a scope block to see the position of the system. Now the only remaining block is the friction block. And if I double click on it, you see I have all these settings which I have to set. It asks for breakaway force and breakaway friction velocity and Coulomb friction force and viscous friction coefficient. And you can see that it asks for forces instead of, for example, friction constants. And if I ask for the help of this block, here I can see this graph and this equation. This is the force of this block, and it is consisted of 3 terms. The last one is the viscous term, which in our example, we do not need that. I'm going to set it equal to 0. I have talked about viscous damping in my previous tutorial, and there is another block devoted to this item exclusively. So I am going to set this term equal to 0. The next term is going to be the constant force or the Coulomb force. You can see the Coulomb friction in this graph is this horizontal line. And that is why it is called the constant force, since this friction force is not a function of velocity or position. It is just constant, and it only depends on the materials and the surfaces and the roughness of the contacting surfaces. So I need this one. And there is also a Strebeck friction, which I'm going to talk about it later. But for now, you set the viscous coefficient equal to 0, since we are going to neglect the viscous friction. How about the Coulomb friction force? As I said, it was equal to mu times n. And n was m times g. It was the weight of the mass. So g was 9.81 and m was 2 kilograms and mu was 0.1. So I have defined this term perfectly. How about the breakaway friction velocity? Just set it to some small number. 0.1 suffices, but you can go smaller too. I go with 1 times 10 to the power of negative 4. And how about the breakaway friction force? You know, there is a difference between static friction force and kinetic friction force. And the friction coefficient for a static case and dynamic cases are different, but we can take them to be equal in this example, since in our code I did not talk about that case. But you probably know that the static friction is bigger than the kinetic or dynamic friction. So for that case, you can set a bigger friction coefficient, like 0.5, for example. As I said, I do not need to change it now for my example, but this option gives you a more precise result. For example, if you are experimenting in a laboratory, you may want to have this breakaway friction force, but I'm going to take it to be equal to the Coulomb friction force. So this is already good enough for me. Now if I run the model, and I look at the scope, I can see that it is pretty much the result that I expected from my code. So this peak is somewhere around 0.63, and in this graph, yeah, it was around 0.63, so it was the same value. Also, the constant final position of the mass is -2 times 10 to the power of -3, and here it is -22 times 10 to the power of -4, so it is basically the same answer. And that is what I expected. And this concludes this tutorial. Thank you for watching. I hope to see you again next time, and bye-bye.